So let's focus on delta connection. So this is a general delta connection you can observe. So this is the impedance for this phase and this phase. Since all of these impedances are equal, so we can say this is a balanced delta connection. And also these are the phase voltages, and remember one thing, from A to B the notation plus then minus, from B to C the notation plus then minus, from C to A we have the notation plus and then minus. So these are different phase voltages, and also there are line components. These are the line currents associated with three lines, and from one line to another line we have line voltages as well. Now similar to our previous cases, we can consider the impedance as R phi plus minus jx phi. So plus minus, that means it will depend the component whether it is a inductance or a capacitance. For inductance it is plus, and for capacitance it is minus, and this is a general expression, that means we have written it just plus minus. And we know for delta connection load our phase voltage and line voltage both are equal, that means V phi equal to EL, but the phase current and line current, they are not equal, and we know that the phase current is line current over √3. So the expression are similar to our delta connection. Let's focus. So first of all, the average power, we can write the average power of each phase as previously our expression was exactly similar to this, that is V phi I phi cos phi. And so if we want to convert that theta equal to 0 degree, then we can write it V phi equal to VR. So this is VR I phi cos 0 degree, then it will appear just VR I phi. So this is VR and this is V phi. So remember this, these are different. Also we can write it VR square over R phi or I phi square into R phi. And again I am recommending this first expression whenever you want to solve different maths. So again, if you want to convert these phase quantities into line quantities, so you can just put the conversion formulas. So here, okay, so here these values has given. So first of all, the total power we can write 3 multiplied by that single phase. So now it is 3 V phi I phi cos theta, and then you know that for delta connection V phi equal to EL, that is written here, and also I phi equal to IL over √3. So now the equation appears as √3 EL IL cos theta. So it is exactly similar to our balanced Y connection. Now the reactive power, so previously our expression was just like this, that is V phi I phi sin theta, and theta is the angle between V phi and I phi. So this is for each phase. So for the total reactive power will be 3 multiplied by that single phase, and again if you convert these phase quantities to line quantities, so the expression is just like this, √3 ELIL sin theta. And if you remember, our previous calculation was just similar, that means for Y connected load we have shown similar expression like this, Vx I phi Vx square over x phi. So these are similar, just same thing is written for delta connection. And now the apparent power, so we know the apparent power expression, which is just V phi multiplied by I phi, and the total apparent power is 3 multiplied by our single phase apparent power, so this is 3 V phi I phi. And again if you put the values of V phi equal to EL, since it is the delta connection, and I phi equal to IL over √3, so it appears just like √3 EL IL. So this was the exact expression for Y connection as well, so there is no difference in final expressions. And now the final expression of power factor. So power factor, we know the ratio of real power to apparent power, so it appears as cos theta. So far we have shown both power expressions for both Y connections and delta connection. Now if I summarize, so all the equations are same for both Y and delta, so there is no difference between the final expressions. That means whenever the average power or reactive power or apparent power, it doesn't depend on whether it is a delta connection or Y connection. The final expressions are all are same, but the derivation was little different, since for Y connection we know that the line current and phase current are equal, whereas the line voltage and phase voltage are not, whereas for delta connection the voltages are equal but the current are not. So these difference introduce some changes in the derivation, but the final output is same. So we can say that the power, which is 3 times if written in terms of phase voltage and phase current. So you can see that in terms of phase voltage and phase currents, it was 3 multiplied by here. So it was 3 multiplied by V phi I phi. So in terms of phase components, it is 3 multiplied by single phase power, and in terms of line components, it was root 3 times. So this is our total expressions, and these are simpler expressions, so I think you can easily remember these expressions. Now we will focus on some example math. So first of this one, this is example 24.6. so for the delta Y connected load, find the total average reactive and apparent power, also find the power factors. That means all the equations that we just noticed, we need to calculate all these values. So this is a complex circuit where both delta and Y connection are available at a time. So we can solve 2 ways. First of all, we can convert this delta to a Y connection, and then this Y will be parallel to our existing Y. Then we can use the parallel resistance equivalent circuit, and then we can determine the power of that Y branch. Also we can convert the middle Y connection to delta, so that will appear just another delta here, and then we can determine the equivalent resistance, and then we can use the power equations for that delta connection. And another approach could be considering that Y connection and delta connection separately, and then we can add the powers. So we will focus the third approach here. So first of all, consider the Y connected load. So only Y connected load is redrawn here, and delta connected is omitted first. So these are all here. So this is more like a superposition theorem, although it is not superposition theorem. So we are just considering a Y connection first and omitting the delta one. So now the Y connection is available, and if you notice, this is a balanced Y, since all the impedances of all 3 branches are equal. We have a 3 ohm inductance and 4 ohm resistance in each branch. So the impedance we can write 4 plus 3j, and then if you convert it to this polar form, so it is 5 angle 36.87 degree. And now the voltages. So line voltages magnitude is 200 volt, it is written here, and so if you convert this line voltage to phase voltage, since it is a Y connection, so it is just 200 over root 3, which returns 116 volt. And now we will just use our previous expression, the simple maths. So the magnitude of line current, which is IL and I phi, both are equal since it is a Y connection, and it is just basically our phase voltage over the phase impedance. That means we want to calculate the I phi. So this one, so I can write I phi equal to this V phi over this impedance. So this is simple calculation. So here this is calculated. This is the magnitude only considered, since in the power equations we only need the magnitude. So that's why in power equations this value is given. So we know the power equations 3 V phi I phi cos theta. So we need this cos theta. So theta can be found from the angle of the impedance. So here the angle of impedance, if you notice, it was 36.87 degree. So that is our theta. So this is our theta. So now we can put these values, and it appears as 6436.6 watt. Also you can use the other formulas, but I recommend you to use the first one. And also you can calculate the reactive power in our previous formula, which was 3v phi I phi sine theta v, and the sine theta is the angle or impedance angle that we have showed it to 36.87 degrees. So if you put these values, it will appear the volt ampere reactive. And remember, for this Y connection we have inductance other than capacitance. So since it has inductance, so it is inductive reactive power. So that var could be either inductive or capacitive, and you know that the inductive and capacitive var are just opposite to each other. So that's why it is written var L. So that L in that first bracket is denoting that this var is inductive var. And our final which is the power factor, so it will be calculated later, since we need to consider both Y and delta connection together, because the power factor will be, you know, on the effect of both Y and delta connection. Now if you consider the delta load only, and in the delta load we have a capacitor of 8 ohm and a resistance of 6 ohm, so we can write the Z delta 6 minus 8J, from where we will get the you know, impedance angle, that is our theta. Here it is written. And this is our line voltage, and this is our, you know, phase current. So phase current is just the V phi over the Z delta, that is here shown 10 ohm, and we only need the magnitude in our formula, that's why angle is you know, excluded here. So the line current is calculated using just like this formula, √3 into I phi, and then we can use our previous formulas, that is the PT delta, that means the real power, 3v phi I phi cos theta. And also if you want to use the line component, then it should be √3 VL IL. So anything you can use, √3 VL IL cos theta. So you can use that on as well, that will be no problem. And the delta, the QT delta, that means our reactive power, so it will be 9600 amperes. And if you remember, it was only capacitance in our delta connection. Let me show you again. So only capacitance is present, that's why this reactive power is var of C, that means volt ampere reactive, and it is only capacitance. So so far we have calculated all the powers for both delta connection and Y connection. Now the total power, we can write PT, it is equal to PTY plus PT delta, since the Y components are also you know, absorbing those power, and also the delta connection are absorbing this power, so we can add those two powers, and this is the total power of our given circuits. And the reactive power, remember, the reactive power of inductive and the reactive power of capacitive, these are just opposite to each other. That means we can't add these two, we need to subtract. And in our calculation, the QT delta for delta connection, the var is larger as compared to Y connection. That's why we have given to QT delta minus QT Y. Since QT delta is larger, that's why our final expression is var capacitance. So finally the capacitance effect is present in the circuit, and it is the var that is asked, that is the total reactive power. And then you know that the total apparent power, we can write PT square plus QT. This came from the you know, the power triangle. So if it is the PT, that is the you know, real power, and if it is the reactive power, then we can write this one is the apparent power, which appears as PT square plus QT square. And our final power factor, so I can write power factor equal to PT over ST, so which appears at 0.94 if you divide this, and it is leading since you already noticed that our capacitive var is present at final. So there is a example math, you should perform this as a homework. So I can end it here. Thank you everyone.